In our baseball example problem, this is a classic problem because not only do you have something going up and down, but it's going up and down and hitting the ground, okay? So here we have a baseball thrown vertically upwards, assume up to be in the positive direction with a speed of 16.8 meters per second from a height of 1.34 meters. How long does the ball take to hit the ground after it reaches its highest point? What's tricky about this problem is we're not just saying up and down, okay? Then you can just use symmetry. It's a piece of cake. In real life, it's realistic that a projectile will leave from a higher point, whether it's a basketball player taking a jump shot, baseball player throwing a ball, volleyball player spiking, etc. Okay? So in order to have success, let's do our 4-step process. Step 1, we make a little what? Sketch, okay? And in this case, the sketch is very important because this helps you visualize how you're going to break down the numbers, okay? So here we have a baseball. It's initially tossed straight up. And the old saying is, what goes up will what? Come back down, exactly. Piece of cake, right? It's going to hit its peak, come down. And here's what's tricky. It's not just coming back down to the same level. It's actually doing what? It's going to go all the way and hit the ground, okay? So right away, this is a little hint, okay? In order to solve this problem, you're going to actually have to break this up into 2 segments when you solve, okay? But the picture is going to help you see that. Got it? Next, let's put on our information, okay? The ball is tossed upwards with a speed of, in this case, 16.8 positive meters per second. That means at this point, it's thrown straight up at positive 16.8 meters per second, okay? But while we're at it, why don't we use a little symmetry? If I throw something up at 16.8, what do I know about how fast it's going to come back down to my hands? We just went over that yesterday, right? If I throw it up at 16.8, it'll come back to my hands at what? At negative 16.8. Good job. Okay, it's going to come back at the same speed, but in the opposite direction. Okay, and that's because gravitationally, it's the same acceleration, the same field that slows it down on the way up that speeds it up on the way down. Symmetry there, yeah? Next, it's thrown from a height of 1.34 meters. So that's the height of the baseball player's hands where it's released, 1.34 meters. Okay? So that could be our delta x we'll use probably for the last part for solving them. Okay. Step 2, what do you want to do? Break down all of your, what do we do in step 2, guys? Our knowns and unknowns, okay? And I know a lot of people find this part very irritating. However, I would put forth to you guys that this is actually the key, the crux to solving all these problems, okay? In the end, algebra, that's easy for you guys. You guys are good at solving for x. In fact, that's all they do in your math classes. They just hide x from you for like 4 years. Like, oh, x is over there. It's in algebra. Oh, wait, it's in trig. Oh, it's in calc, whatever, right? So don't worry about the math part. It's the ideas we want to focus on, okay? So how do you guys want to approach this problem, okay? Notice there are 3 segments to the ball's trajectory. Going up, right? Coming down to the same level, and then coming down to the ground. What's the part we actually care about? There we go. What's the part we actually care about? Do we care about going up? No, what are we trying to figure out? We're trying to figure out how long it takes the ball to go what? All the way to the ground, okay? That's what we're trying to figure out, right? From the peak. So we're going to solve for here, okay? Going down. We want to just solve for down. And you know what? I'm going to break this up into 2 parts. Down 1 and going down 2. There we go. Because there's actually 2 parts to this trip. You see that? Okay? Then that'll make it easier. So why don't we do down 1 first? Okay? Down 1. So if we're just going to solve for going down, at the very peak, little trick, what can you call the initial velocity at the peak? Big fat 0 meters per second. Because for a brief instant in time, as the ball goes up, it has to slow down to 0 before it can come back down. Got it? Next, do we know VF? Do we know its speed at this point? We do, right? If we throw it up at positive 16.8, it's going to come back to your hand at what? Negative 16.8, okay? And I was helping somebody this morning. They were like, how do you know what VI is? It's always 0, right? And I'm like, uh-oh. Okay, you don't memorize. You apply the idea. VI, it just means the speed at the start. And VI is whatever you want to pick. If you want to start here, if you want to start here, if you want to start here, it's whatever you want to pick. Okay, it's free country, but you just want to be logical and consistent. Got it? Next, what's another known or unknown? How about this one? It's always a freebie, usually, and that is, which planet do we live on? We think we live on Earth. Welcome, we come in peace, right? And what do we know about Earth? Actually, you guys did a good job measuring this last week. Acceleration due to gravity is negative what? 9.8 meters per second squared, okay? Yeah, we had good results when we went out to the football stadium and chucked stuff off the bleachers there, yeah? What else do we know? Delta x and what? Time, okay? Delta x in this case would be this distance back down, right? This is delta x1. We actually don't know that, okay? So we might have to find it, we might not. And actually, I think we actually don't have to find it, because what do we really care about in the end? We're trying to solve for what? How long. So how long is what? Time, right? Let's call this time 1. That's all we really want to care about. Why don't you put a box around that and star it, okay? Half the problem is knowing what the problem is about, okay? So later on, when you guys graduate and get out of here from Hinsdale Central, you may or may not go into nerdy science, become some kind of engineer, medical field, etc. However, will you have to solve problems that are complicated and think logically and know how to communicate? The answer is yes, right? So a lot of physics is I'm trying to teach you guys how to problem solve. So a lot of times, if you know, what you have to work with, and what you don't know, that's half the problem, is focusing it. And notice, what's the little trick? Guys, remember, what actually helps you figure out which equation to use? It's actually what you what? Don't know. Okay, I want to solve for time, yeah? And I don't know delta x. There's only one equation. Real easy. Which one? Which one doesn't have delta x? Nifty number 1, okay? Here's another trick. If you don't know which one to pick, just try one. There's only 4 of them. And only one's going to work eventually. Got it? But I'm trying to make your life easier, okay? And by the way, can you put this on a note card to use on your exam? Why not? Because in real life, you'd probably look up an equation anyway, okay? So I'm not trying to force you to memorize. I want you to understand. That's the goal. That's different. That's weird. You're not used to that, okay? Here we go. Let's break it down. Break it down. Woohoo! So we're going to use, in step 3, nifty number 1. Okay, and someone's like, do we really have to write out the equation? And the answer is yes. I really want you to show which equation you're using. And the reason why is 2 reasons. Reason number 1, helps you learn the equations, VF equals VI plus AT. Reason number 2, you don't do what I call little lotto physics. Okay, already it's helping someone this morning. And this guy was just multiplying and dividing and squaring and square rooting numbers randomly. So it's kind of like, ever see like the little ping pong ball machine for the lottery? It spits out ping pong balls. That's little lotto physics. Don't do that, okay? Don't, 57, 49, square root, okay? Okay? Don't make up your own equations. Let's just shove the numbers in. And you guys are really good at solving for x at the unknown, okay? What do we put in for VF? Negative 16.8. In this case, VI is 0. We're falling from the peak. A is negative 9.8 meters per second squared. Solve for time. Don't worry about units. We already have that. Here's what's cool. Because we call down, down, when we divide by negative 9.8, the 2 negatives become positive. That's important because you can't get a negative time, okay? So let's get out. I'm going to take 16.8, divide that sucker by 9.8, and I'm getting a whopping 1.714. Let's keep a couple decimals. 1.714 seconds, okay? Notice, is that the total time to hit the ground, or is that just the time to come back down to your hands? Which one? That's just coming back to your hands. So to finish this, we got to figure out the second part of the trajectory. I'm going to call this down 2, okay? So again, it's not too bad if we can just break it down. Okay, so let's just break down all of our quantities, VI, VF, A, delta x, and time, okay? So here is where the pedal hits the metal. This is to see if you really understand, okay? If I throw a ball up at 16.8 meters per second, it comes back to my hand at negative 16.8 meters per second, and then it's going to hit the ground. What should I call VI now? At this point, if I'm starting from here, okay, my VI is actually going to be now negative 16.8 meters per second. And someone's like, hey, wait a second, you can't do that because I thought we just said VF was negative 16.8 meters per second. It is because we were solving for this segment of the trip, from the peak to your hands. Now we're doing from your hands to the ground. You see that? Therefore, we can call VI negative 16.8 meters per second. Do we know VF? We don't. We don't know how fast it hits the ground. Do we need to know it? Probably not. So again, 4 steps makes your life easier, so you don't have to solve for something that you don't need to. On your test, don't waste time solving for something you don't need to know, okay? A is still negative 9.8. We should still be on Earth. Gravity shouldn't change. If you can change gravity, you are awesome. Come see me. I will give you extra credit because you'll probably win the Nobel Prize. I'll become your literary press agent. I'll just take like 5% off the top. Nothing else there, okay? Delta x. What can we call delta x? From your hands to the ground? in this case, since they give us the height of the player, it'll be negative 1.34 meters. Why negative? Because the ball's going which way? Down, and then time 2 is what we want to solve for there. Okay? So now, again, it's what you don't know that helps you pick the right equation. There's only one equation that doesn't have VF, and it has time. Okay? Which one? Which one doesn't have VF, but it has time? Nifty number. Aha, okay. See how there's only one that doesn't have my VF, but it has time, which is what I'm trying to solve for, okay? So again, it's what you don't know that actually helps you figure out the problem. That's kind of cool, right? I think so. I'm easily amused, though. Okay, here we go. Delta x equals VIT plus 1/2 AT squared. Delta x in this case is negative 1.34 meters. That's equal to my initial velocity of negative 16.8, right? Times the time plus 1/2 negative 9.8 times the time squared. Oh, no. Bummer. Okay, not too bad. Right away, we're going to have to rearrange this, and what kind of equation are we going to end up with? Can you tell? Half of 9.8 is 4.9. If we rearrange this, this will be 4.9 times t squared plus 16.8 times t. Let's see, bring it to the left side, minus 1.34 equals 0. Anyone recognize this? This is what? Ax squared plus bx plus c equals what? 0. We got to use the, what's that thing called? It starts with a Q. Quadratic formula. What's quadratic formula? You guys remember? Yeah, what is it? Right, okay. So we got to do negative b plus or minus the square root of b squared minus 4ac over 2a, yeah? Okay? So let's go ahead and chug it through. Not fun. We got a quadratic formula. Let's just go ahead and put in the values here, right? So we're going to have negative b would be negative 16.8 in this case. You use your numbers, okay? Plus or minus square root of b squared. So in this case, it would be 16.8 squared minus 4 times 4.9 times c, which is negative 1.34. So the two negatives actually will become positives. That's actually good to know. And then we want to divide the whole thing by 2a, 2 times 4.9, which is 9.8. Okay? So this is just ugly. We just got to put in our calculator. So I'm going to go ahead and do the quadratic formula. You're going to end up with a positive time and a negative time. Okay? Which answer is going to make sense? Do we want to have a negative time? It's got to be a what? A positive time. The negative time actually would be actually this. If you could reverse time, it would be if the ball was launched from the ground. Okay? But that's the abstract meaning. We're just going to use the positive root there. Okay? So I just want to point out that you got to use a little bit of common sense. Negative time is not going to work. So when I do b squared minus 4ac, I get 17.56. So rather than subtracting that, okay, I'm going to add on then the negative 16.8. And then I'm going to divide that by 2a. Divide that by 2, and then also divide that by 4.9. Okay? And then I'll get our final time 2 of 0.0779. Good enough. Okay? So time 2 is 0.0779. So we're almost done. It was a little bit evil because we had to do the quadratic equation. There we go, 0.0779 seconds. And you know what, really quick, let's just use common sense. Does it make sense that time 2 is a lot shorter than time 1? It does, because time 1 was for the ball to go to the peak and come back to your hands. Time 2 is just to go from your hands to the ground. So how do I get my final time? I just add on to that 1.714 seconds, time 1, okay? 1.714. Yep. So my time total is what we're looking for. Time total is just time 1 plus time 2. And I get, survey says 1.7919. Good enough, okay? Which I guess we could round that off to 1.792. That should be enough decimals there, 1.792 seconds. So to recap, why is this the hardest problem? Because it's number 9, the last one there? Now, it's because it's trickier because you're not just solving for one part of the path of a projectile, okay? The ball is going up, it's coming down, but then it's going all the way to the ground, okay? But it's doable. Now, there actually is another way to do it. Oh, really? What? Did I just give you the hardest way? I don't know if this is the hardest. For some people, this is an easier way to break it down, but there's another way to do it, okay? And the other way to do it would be actually to try to solve for the whole thing like this, right? Call your delta x negative 1.34, and then just subtract the time out going up. That's another way to do it, and you'll get the same thing, okay? Some people will like that easier because you don't have to do the quadratic formula. But the cool thing is you'll get the same answer because the 4 nifty equations of motion are all derived from the basic definition of velocity, acceleration, and finding your position based on the average velocity of something accelerating. Okay? In a nutshell, that's the evil baseball problem.